Alright, so we have seen the IC design and detail, which was BM2P016T. So this is the PWM controller which we are going to use to design two AC-DC converter. One will be 15 volt 1.5 ampere and another one will be 12 volt 4 ampere. Okay, so these are the two designs that we'll be doing. In this particular session, we'll concentrate on this particular design and implementation. Alright. So what is the thing that we are going to see in this particular session is we are going to see BM2P016T IC, which we have already seen the design and detail, and then the converter which we are going to design for 15 volt 1.5 ampere. Alright. So as you can see, our aim would be to understand what is the design specification first, and then we will try to design the block diagram and parameter and all those things. Okay. So let me quickly review that. Last time we had seen the design specification for 22.5 watt 15 volt AC/DC converter, which is going to be flyback topology based. Okay, so our input range is 90 to 264 volt. 230 volt will be the typical voltage. Input frequency, output voltage, which is going to be 15 volt. We have maximum power, which is going to be 22.5 watt. Similar to that, other parameters are there. So these things in mind, we'll keep in mind and we'll try to design our AC/DC converter. Okay. So very first thing that we have to do is we have to get into the concept of block diagram. So let me open a block diagram. This is the input voltage that we must have, which is going to be my AC input. Okay. AC input is already written in the block. Then we have safety, which will be fuse and MOVs and all those things. We have PTC also sometimes for low voltage, low power application. Instead of utilizing MOVs and all, that will be very costly. We can utilize PTCs. Okay. Then we have safety capacitors like X2 capacitor, Y2 capacitors, and we have CMC, that is common mode choke. Then we have bridge rectifier. Then this is the most important part, which will be transformer. So however, we will not see the transformer design. We'll directly take the like a standard transformer either from the reference boards or like lot of places are there. I will tell you how to select a transformer for your design. Then we have output rectification, just like bridge rectifier at the input, we have output rectification at the secondary side. Then we have filters and capacitor at the output also. So if you want to filter out your like voltage, output voltage, you can put a filter like ferrite beads or like inductors and all those things. Then we will be designing feedback circuit, and then we will be selecting an optocoupler to send the feedback voltage to the PWM controller, which is having inbuilt MOSFET. So this is a complete block that we will be seeing. So in this schematic, we will try to incorporate each of them one by one, and we'll try to see this particular circuit. So this is the outcome circuit that will be there from our design, and each and every component we will try to select based on the calculation that we will do. Okay. So let me show you like the first calculation that we will be doing. So the first calculation is going to be component selection process. So for that, what we do is we try to see what will be my rating of fuse, my bridge rectifier, my MOVs, all those things we'll try to select. Okay. So first of all, let us consider this particular formula, which is going to be my P input is equal to basically P output, that you guys know, right? But since there is a efficiency, so we will be having eta times P input is going to be my P output, which eta will be always less than 1 or less than 100%. Okay. So this is how you already know that my P input is nothing but V input into I input, and similar to that P output is nothing but V output into I output. So if you expand this, you are going to have P output is equal to V out into I out divided by eta. That will be equal to P input, that is V input into I input. Okay. Now we will put it V in I input is going to be equal to V input will come down, and let us consider eta right now for 80%. So that is going to be 0.8. So it means what will be there? What will be there? 15 into 1.5 ampere divided by 0.8 into V input. Now let us consider V input is 85 volt to 265 volt. So what will happen if you consider in V in DC voltage? So that will be 85 root 2, and similar to that 265 root 2. Okay, 265 root 2. So 265 root 2, if you do, it will come 375 volt, and this will come 120 volt. Now, can you guys tell me that my I input maximum will be happening when my input will be minimum? That V input is minimum, my I input will be maximum. That maximum current will be drawn from the AC or the mains. Okay. So the AC mains will be having maximum current that will be drawn is 0.234 ampere. So this is the parameter that you have to keep in mind, and you have to select a fuse based on this. So let us say if you are going to select a fuse of rating, let us say 0.234 ampere, so it may fail. So you have to keep it either like 2-3 times more. So let's say 0.75 ampere will do, or even 1 ampere will do. So for our simplicity, we will take out, let's say, 2 ampere fuse or maybe 1.6 ampere fuse. That will be more than enough. Similar to that, bridge rectifier rating will also, we will try to take more than this. Okay, so basically we'll take up, let's say, 1 ampere rating or maybe 2 ampere rating. So this actually gives us an understanding or a foundation to select a particular component based on our circuit design. All right, so this is what we have done. So what I have done is I have listed down each and every parameters that we will be taking up while designing the power supply. So while designing the power supply, we have to have these components like AC input. So input connector we need. Then we need fuse. Then we need transient suppressors, that is metal oxide varistors or MOVs. Then we have safety capacitors like X2 capacitor, Y2 capacitor. Each and every like component you will be seeing in the circuit. Okay, so as you open your circuit, you will see you have like a AC input or AC input connector, then we have fuse, then you have MOVs, then you have X2 capacitors. Similar to that, X2 capacitor will be one more here maybe. Then we have bridge rectifier, we have CMC here. Okay, common mode choke. Okay, so these things will be seen. So that's the reason I'm telling you that list out all these things, so while designing you do not miss out any component. So common mode filter, then we have bridge rectifier, we have bulk capacitor, or this is also called as DC link capacitor or input capacitor. Then we have snubber circuit. So snubber circuit is basically, we have already given you like lot of concepts about snubber circuit and why it is used. It is used to reduce the ringing or reduce the transient at the primary side of the transformer. Okay, so actually that reduction or flyback like voltage saves my MOSFET. Otherwise my MOSFET may fail because of very high voltage. Then we have transformer. So flyback transformer will take up a standard transformer. Then we have controller IC. So my controller IC is nothing but your PWM controller that we have already selected, which is what was that? Let me just write out BM2P016T. So this is the IC that we are going to use. Okay. Then we have output rectifier. So again, we will need to find out one diode and what would be the capacity or what would be the rating for that diode. We have filters and capacitor at the output side. Then we have feedback circuits and voltage references. So basically, we'll try to use TL431 as I have given you the concept for this as well. And then we will be taking optocoupler which will be sending my feedback voltage to the input side. Okay. So now let us do one basic calculation. So what we'll do is, since we have the output voltage at 15 volt, so you know that my cathode to anode voltage will be 15 volt. This is what we have to regulate at the output. Okay. So let us say we are going to put R1 and R2. So my R1 and R2 value has to be defined in such a manner that my Vx value will be 2.5 volt. Okay. 2.5 volt. This is the main understanding that you should have, or otherwise 2.495, that is the thing that they say always V reference. So my VKA is going to be equal to V reference into 1 plus R1 by R2, that you have already seen this particular formula in previous sessions. Now let us put the values that we know so that we can calculate other resistors. So we already know that my V reference is 2.495, Vk is 15 volt, and based on that let us consider my R2 value is 10 kilo ohm. Okay, so in 10 kilo ohm we will be able to find out my R1 value as 50.12 kilo ohm. So if you calculate this, you are going to get this much. It means What would be the current that will be flowing in this particular branch? Let us say Ix. So Ix is going to be flowing through this R1 and R2 will be how much? 15 divided by R1 plus R2, that is around 0.249 milliamperes. Okay. So you have to make sure that it is like more than 0.1 milliamperes. Otherwise your like TL431 will not even trigger. So TL431 needs some amount of current, otherwise it will not trigger. Okay. So you can keep this current as around like up to around 1 milliampere or something, or even lesser than that is fine. Okay. So this is what the understanding is. Otherwise, you will tell that, sir, I can utilize here 100k or 200k. In that case, R1, R2 will be very high, and the current that will be flowing, which will be Ix, will be very, very low, and which will not be able to trigger even if the voltage is 2.5 volt. Okay. So that's the understanding you should have. Otherwise, it will not trigger. Okay. So good. Two calculation we have done. My input selection like fuse and bridge rectifier and all those things. Then we have already calculated this particular voltage feedback circuit. So what we'll do is this 50 kilo ohm. What we can do is we can convert it into two resistors. Okay. So R1 can be converted into, let's say, RA and RB, and RA plus RB will be 50 kilo ohm, and similar to that R2 will be down. Okay, so this is how what we will try to do. So this provision will make like us eligible, or make us little bit advantageous to select a different resistor to suit this particular resistance value. Okay. All right. Now let us do the circuit. So as you can see in the circuit, what I have done is I have selected a 2 ampere fuse. So 2 ampere fuse, what are the selection criteria that you already know? In the component selection process, I have told you that the rating of this particular fuse must be, let us say, 300 volt AC, because 230 volt or 265 volt AC it will be working. So I don't want it to fail below 300 volt. So 300 volt AC I am taking 2 ampere rating for AC DC application. Similar to that, MOVs also, if you want, you can like quickly check it. So what will you do? You can check this particular part and go to, let's say, digi key. In digi key you can find it out very easily. So you can see we have 470 volt 2.5 kilo ampere ratings. Okay, so this is the IC that is there with this is the varistor, or this is the metal oxide varistor that is there from little fuse. All right. Good. So this is what, otherwise anyway I have given you complete bill of material. We will try to see once we start designing the circuit, we will try to see what is my BR1, what is my C1, C3, C4 and all these things. What is my MOVs like RV1. So all these things are there. Okay. So you don't worry about this. We have all the resistors, we have all the test points, we have my ICs, and then we have like my optocouplers. Then we have TL431 IC, that is voltage reference IC. Okay. So all these things are there with us. Now let us try to find out other parts. So other parts, as you can see, what we are going to do is we have the X2 capacitor, which is 220 nanofarad. Then we have this resistor, which is actually like used for avoiding the shock or something, because what happens is, let us say you switched off your circuit, so line and neutral is gone. So in that case there will be like charge that will be stored in the like X2 or Y2 capacitors, and as well as this particular bulk capacitor. So they will not have any path to discharge. So this particular resistor will help them to discharge quickly. So that's the reason you will not have any shock. So basically this is actually used in your medical device grade power supplies. Otherwise other power supply, this you will not see, because they do not matter. You are not going to touch them, right? Then we have common mode choke, which is going to be 15 millihenry. This is the common mode choke. And then we are going to select one bridge rectifier. Okay, one more thing. This is my X2 capacitor. This is C1 is my X2 capacitor. C15 and C16 are my Y2 capacitor. Okay. So actually, as you can see, my X2 capacitor is between line and neutral. Okay. So between line and neutral, it is connected as X2 capacitor. and my Y2 capacitors are connected from line to ground and neutral to ground. So this is what you have to have an understanding. So you can see X2 capacitor between line to neutral and Y2 capacitor between line to ground and neutral to ground. Now, how this particular circuit is working, let me just give you quickly, the flow. So let us say, anyway, you already know that, let us say this is my line, AC input. So positive cycle, what will happen? This is coming positive cycle. So this positive cycle, it will start from here, and this it will see like this and go like this, and this is the capacitor that is coming. Okay, so this is what it is going to come, and then what will happen? This particular diode will be there, and this is the input that is going to neutral. Okay, that's all. Now coming back to the positive half cycle, negative half cycle. So negative half cycle will be this. So in that case, actually, current will start from neutral. So it will start from like this, and then what will happen at this junction? So at this junction, it will come from this particular diode. So this particular diode will be forward biased. Again, the same path it is taking, coming back, okay, to this ground, this terminal, and from here it will enter both side, either like a down diode or up diode, both, but it will go to upper one because down is higher. So it will go like this and then go back to your line. Okay, so this is how the path is there for positive half cycle and negative half cycle. Hope you have a good understanding about this path, and this is how the capacitor C6 is getting charged. Okay. So one method is, like you have already seen how to calculate this particular value of capacitor, which is C6, that is 47 microfarad. Another method that you can like try to follow is, go to your PI expert, as I have already told you, and design a 15 volt 1.5 ampere rating power supply AC/DC converter using flyback technology or flyback topology, and see what is the value of this capacitor. That is the quickest way to find out the value of this capacitor. Similar to that, even RCD circuit values you will be able to find out from that reference very easily. So that is a another method I am trying to give it to you. Otherwise you can always calculate based on the methods that I have given you. Okay, good. So this was all about this. Now let me see what is the diode that I have chosen. So this diode rating is how much, that we'll just quickly see. So you can see this particular diode is of rating uh, 1 ampere. So 1 ampere 1 kV. Okay, so 1000 volt rating with 1 ampere. If you want, you can have 800 volt rating also, not a problem, but 1 ampere is minimum needed, otherwise it may fail. If you want, you can go ahead with 2 ampere as well. So this is the diode that is taken from diode incorporated, and it looks like this. Okay, good. Coming back to the RCD part. So RCD part, as you already seen, how you have to do is, you go to PI expert and try to design this particular circuit and see this particular value. So always you can see that my C20 is all, like C is always 10 nanofarad. So it can be from 1 nanofarad to 22 nanofarad. Okay, so basically 10 nanofarad always meets all the spec. So only challenge that we try to find out is resistance. Okay, so this resistor value is actually needed, and this diode and resistor is not a problem. This you can anyway find out. This transformer, I have taken it directly from the reference design. So you can also take that same, or otherwise once you are designing using PI expert, power integration expert tool, so from there, whatever the transformer that is suggested, you can take that one. Okay. Coming back to this capacitor, so this is also again Y2 capacitor, or this is also Y2 capacitor. So from primary to secondary, if you want, you can keep this thing. So this is a leaking capacitor, or it will give you a leakage. So it is actually used to actually it is going to give a leakage to your circuit, but it saves your for EMI/EMC testing. So this is how it is advantageous. So you understood primary side RCD snubber, and then now coming back to secondary side. So secondary side we have RC snubber or RC clamping, then we have the secondary diode that is there. So this diode is there. Then we have secondary side, we have capacitors. So this 330 microfarad capacitor and 10 microfarad capacitor, zero point 0.1 microfarad capacitor is put. If you want, you can have a provision for one more, like a 330 microfarad capacitor. But since the current rating is very less, like 1.5 ampere, so 330 microfarad is enough. However, I have given you a technique for how to calculate the output capacitor value. So 330, you will see that 330 is more than enough. Okay. These filter capacitors are actually used to like reduce the ESR value. So that's the reason we always try to give zero point 0.1 microfarad or something like that. If you want, you can remove this, make it as DNP. And one more thing, if you want more filter or something, you can put ferrite bead here. Okay. So ferrite bead, or like around 15 microhenry inductor you can put with proper current rating. So around 3 ampere current rating you put minimum. Okay. Chalo, and this is the output connector that is there. So as I can tell you, like these output connector and input connector have been properly chosen. So if you want, you can go and see. Like this is, I think, 3.6 millimeter. Yeah, 3.96 millimeter rating. Sorry, pitch size. So this is the connector that is used at the output, and at the input, I have used actually like terminal block type. So terminal block, already that you can insert the mains and neutral, like line and neutral lines in the slot, and you can tighten it through the screw. So this is how it is there from Phonics. Okay, so that another connector was there from JST, and this is there from Phonics. So hope you have now a clear idea of how to select components for different parameters. Okay. Now, let us move back next. So next we are going to design the TL431 feedback circuit. So see, this is the 15 volt that is there with us. This 15 volt that is there with us, we have to regulate that. So that's the reason we tried calculating the resistance value. So this was 50 kilo ohm. So 47 plus 3.3, that is 50.3 kilo ohm I have put at R1 as R1. So R1 is nothing but a combination of R3 plus R5. Similar to that, R2 is 10 kilo ohms. That you can see, R7 here is 10 kilo ohm. So don't worry about the reference designator. It automatically gets assigned. So that's nothing but coming up like that. Now this particular branch is going to get connected to the reference of the TL431. So this TL431 is coming here, and then this is going to get connected to the cathode of the optocoupler, and optocoupler is used here VO615A. So this is a like a 4-pin IC which is used to like isolate the secondary side and primary side and give the feedback voltage to the feedback pin of the controller IC. Okay. Now slowly we are moving to the controller IC place. Let's keep doing that. So this was the feedback part, and this is the like fast lane. So fast lane is making sure that the current that is flowing through this particular IC will be how much? 15 by 1 kilo ohm. So basically it makes sure that the current that is flowing into this cathode to anode is around 1 milliamperes. So that's the reason you can see, let's say voltage drop across this particular diode is 1 volt. So 1 volt by 1 kilo ohm, that will be 1 milliamps. So 1 milliamps is flowing through this. And this is the RC circuit that is introduced to have extra like poles and zeros. Okay. So that's all. Coming back to the like primary side of the controller part. So as you can see, the controller part, what is happening is the auxiliary input is going to supply a voltage to the VCC pin, which is going to be 15 volt through this particular diode, and like resistor is put in series to like protect the input pin. Okay. And a 10 microfarad capacitor is used. If you want, you can add extra zero point 0.1 microfarad. Okay. But 10 microfarad is more than enough. You must have at least one capacitor to the VCC pin, otherwise it will not work properly. Okay. So minimum connect 10 microfarad or plus 0 0.1 microfarad additional. This is the ground line, so that is connected here. Then we have F adjustment that I already told you. So we have like frequency hopping was there, or frequency reduction was there. So all these things was there. Burst mode was there. So for that, one capacitor is needed, which is 1 nanofarad. Coming back to the drain pin. So drain pin, my primary side transformer is connected, that is pin number 3 is connected to the drain of the MOSFET. So this is drain of the MOSFET, and internally there is a MOSFET here. So this MOSFET is getting connected to the source now. So this source, MOSFET drain is connected to the primary of the transformer, and then source is connected to the ground. So source is connected through to the ground with a current sense resistor. So current sense resistor, you can see we have R11 and R12 with a parallel circuit. So that is 0.82 divided by 2, that is 0.41 ohm. Okay, so this is the current sense resistor that is used for this particular PWM controller. So all right, hope you have now a clear idea of how to design this particular circuit of each and every parameters. Okay, so let us quickly do one thing. I'll just open a ORCAD, and in this ORCAD we have already seen how to create a project and how to start our circuit design. So as you can see, I have this page 1, and you can connect add your library by add files and connect your this thing, and you can see we have all the parts that is there with us. Okay, coming back to the circuit design. So circuit, you can put the each and every part. Let's say if you want to put a fuse, so put a fuse. I have already taught you how to put. Okay, if you want, you can put this kind of fuse, or another kind of fuse is also there, which I have put here right now. Let us say fuse. So see, this type of fuse is there. So whichever you want, you can do, and then you double click that and change the parameters. Okay, so double click that, so you will have a open a pivot table. So this parameter you can change based on your requirement. All right, so what is your requirement, like who is the manufacturer and what is the manufacturer part number. So as you can see, this is the fuse that has been used. So let me open DigiKey and tell you like what is the fuse that it looks like. So this is the fuse that is been used. It is actually used for my 2 ampere rating 300 volt AC. Okay, so this is the fuse that has been used in our circuit. Come out. Similar to that, we have MOBs, we have test points for line and neutral. If you want, you can increase the size, and if you want, you can put some text also, like what is your pen, like a main power supply. Danger I have kept as a some notification or some cautions. Then we have these resistors. Coming back to other parts, you can see all other parts are properly put. Okay, so coming back to next part is how to develop the bill of materials. So in circuit entry method, or how to enter circuit in ORCAD, I have taught you everything. Try to follow the same thing. Otherwise you can go to bill of material, put your headers and put your combined properties properly, enable this open in Excel and open it, so you will be generating your bill of materials. Okay, so all right, this is what I wanted to show it to you in the ORCAD directly. And for ORCAD, we have tried using open source for from TI, which is PSpice for TI, that is available. Now coming back to the bill of materials. In this bill of material, you can see resistor, capacitors. I have already put all the values from our database. Okay, so we have R3, let's say 47 kilo ohm, that is a stack pole, which is going to be 47 kilo ohm 0603. One more 47 kilo ohm is there, that is actually 0805. That's the reason that is different part. So similar to that, other parts are there. So what you have to do is you have to follow same process all the time. Okay, so try to keep these parameters. You can remove this right now. Try to keep always these parameters, like you have to have a PCB footprint, so that PCB guys can understand what is the information that is needed. Then we have description, so that it tells you what is the part, like what is the complete description about that. Let me come from the left side. So we have like item numbers 1 2 3 4 5, like that, how many quantities are needed. So you can see capacitor is needed 3 times, 3 capacitors. We have reference designator, then we have part number, we have manufacturer. If you want, you can make it as okay, part is nothing but it is just a value kind of thing, but this is the manufacturer part. Okay, so this part is not the manufacturer part, actually this part is the manufacturer part. So manufacturer part, then description, and then PCB footprint. All right. So this is the way you have nicely developed your bill of material, your schematic PDF and everything. So hope you have now a clear idea of how to design this particular circuit. So now my recommendation would be to go and complete this particular circuit design in your PSpice 4 Ti, and so that you can like understand how to design from beginning to end, so that you can have a proper understanding and experience as well to enter the schematic into the arcade. Okay. All right guys, thank you.